The next unit we're going to be looking at has to do with chemical reactions, but in addition, how to perform calculations that are revolving around chemical reactions, and that's going to be called stoichiometry. Now, this is one of the fundamental units for the year, so for those of you that have intention of going into Chemistry 12, this is going to be something that you really want to work on. So what are chemical reactions? We're going to do a series of demos around the room in class next day, and one of the things I'm going to ask you to do is observe properties that make you realize that a chemical reaction has happened. One is that you can have the emission or absorption of heat. In other words, you get a temperature change. You can get the emission of light. You can have a change in color. You can get the production of gas, although I don't like to think of this as the best particular option because it can also be an indicator of a changed state. And you can have the formation of a precipitate, which is a solid that comes out of a solution when two solutions are mixed together. Now, chemical reactions have to be written and represented so that we can communicate them in an easy way from one person to the next. And in order to do that, we use a chemical equation. In chemical equations, we always write the reactants on the left-hand side, the products on the right-hand side, and an arrow goes in between them to indicate that there has been a change, or in other words, to say the word yields. Now, we're going to come back to a law, which we've said before, and that's that there's the law of conservation of mass, or the law of conservation of matter. And what that law says is that in an ordinary chemical reaction, the sum of the masses of the reactants must equal the sum of the masses of the products. In other words, matter is neither created nor destroyed, it just gets transformed from one type to another. Now that sounds very similar to what we talked about with the law of conservation of energy. In a physical or chemical process, energy is also neither created nor destroyed, it just gets transformed from one type to another. Now, why is that law of conservation of mass important? Well, what we see, and we're going to go back and you'll do some practice problems later in Hebden. What you're going to see is that this is the basis of writing and a very important part of our chemical reactions. Now, before we have a chance to do that, we have to talk about what happens to the bonds as a reaction happens. And what we see is that chemical bonds hold atoms together in molecules of compound. During a reaction, the bonds between reactants break. Now that has to happen in order to allow those atoms to rearrange. And it also allows, once they have rearranged, the formation of new bonds, producing new products. Now, chemical equations, like I said before, help us to describe the process in a shorthand form. So let's look at a quick video, and I want you to watch for what are the reactants, what are the products, what does the arrow mean?
It is possible to describe a chemical reaction in words. For example, we saw how sodium bicarbonate and acetic acid chemically react to form carbon dioxide gas, sodium acetate, and water. Scientists had developed a simpler way to present a chemical reaction. Using the chemical symbols for compounds, a reaction can be expressed by a chemical equation. A chemical equation is an expression using chemical symbols to represent a chemical reaction. In a chemical equation, the plus sign is used to show that substances combine. Between the reactants and products, an arrow signifies that reactants yield or result in the following products. Let's take a look at an example involving the element copper, seen here in this bucket. Copper is often used as material for roofing and for downspouts, seen here. With time, the shiny copper metal turns green, symbolizing a chemical reaction between the copper and carbon dioxide in the air. The reaction can be symbolized by the chemical equation Cu plus CO2 yields CuCO2. In chemical reactions, the overall mass of the substances reacting does not increase or decrease. The changes that occur in a reaction involve the rearrangement of atoms, not the destruction or production of matter. This is expressed in the law of the conservation of mass, which states that mass cannot be lost or gained in a chemical reaction.
Once we've written a chemical reaction down, we have to balance that chemical reaction, and that was the importance of the law of conservation of matter. We can't have different numbers of or masses of matter on each side, so that means we have to have the same number of atoms of each type on each side. So in order to do that, we use coefficients when we balance. Coefficients are the numbers that you place in front of an atom or a molecule that tells us how many of each atom or molecule are present. So in this particular case, for example, we have 2 hydrogen molecules and 2 water molecules. If there's no number written, remember there's an invisible 1 there. Similarly, we have 2 atoms of sodium and 2 molecules of sodium chloride. Anytime you have more than 2 atoms attached together, that's considered a molecule. So the first thing we need to do is remember how to balance single elements. And in general, what I suggest to people is that you balance the single elements last, always keeping hydrogen and oxygen, if possible, until the very end. So I'm going to show you right now what's called the ping-pong method. In class, we'll go through a second method which helps us to have a chart, which is good for people that are a bit more visual. So on the left, I have 1 sodium. I'm going to bounce over to the other side, and I see I have also 1 sodium. Great. Looking at the oxygen, I have 1 oxygen atom. Bouncing over to the left, I also have 1 oxygen atom. Now, the last one is hydrogen. And what I see here is that I have 2 hydrogen atoms. And on this side, I have 1 plus the 2 gives me 3 hydrogen atoms on the right. This brings me to what I call a fundamental suggested rule of balancing chemical equations. And what I've said to people and continue to say is that when you have an odd on one side and an even on the other, you have to double the thing that's making the one side odd and start the whole game over again. So in this case, we've got our odd side is the right-hand side, and the part in particular of the right side that's making the right odd is this. So I'm going to double that number and start again. So now I have 2 sodiums on the right. Bouncing over, I'm going to throw a 2 in front, so I've got 2 on the left. Looking at the right, I also have two oxygens now on the right, which means I have to have two of the water molecules to get two oxygens on the left. Now looking at the hydrogen, I have four hydrogen, two in each molecule, and I've got two molecules, so that gives me four. And I've got two here in the sodium hydroxide and two in the hydrogen, so that happens to be balanced. When we look at the next kind of reaction where you have oxygen, carbon dioxide, and water, we'll look at how to classify that later, but for right now you might remember from last year that it's called a combustion reaction. These tend to be the hardest ones to balance, but again, if you can just kind of play back and forth, balancing them out as you go along, everything will work out for you. So I see that I've got one carbon on the left, one carbon on the right. I have four hydrogens, so I have four hydrogens on the left and only two on the right. So I'm going to double this water molecule so that I've got four hydrogens on the right. Now looking at the oxygen, I have two oxygens here, and 2 plus 2 is 4 on the right, which means I need to double the oxygen again. Notice how I've left that single element to balance until the very end. Sometimes what we see is that it's easier for people to use fractional coefficients first and then change the fraction to a whole number by multiplying everything by the denominator. In general, we'll see that this is a 3. This tends to be confusing for people. So I kind of tend to suggest that you avoid it, but if that makes sense to you and you're like, oh yeah, I've got 7.5 oxygen molecules, obviously you have to multiply everything by 2, then that will be okay. Now the coefficients have two different specific meanings. One, they can represent the number of atoms and molecules in a reaction. They can also represent for us the number of moles of atoms or molecules, which for us we know is a logical choice because moles are an easier quantity for us to measure and to use. So reading that statement at the bottom, that chemical equation, I can either say that two hydrogen molecules and one oxygen molecule produce two water molecules, or I can say that 2 moles of hydrogen gas and 1 mole of oxygen gas react to produce 2 moles of water. Now each reaction happens to involve different substances that are in different states, and you should already know how to indicate those states, but remember that we use subscripts, and in particular those subscripts happen to be that an L represents a liquid, a G represents a gas, an S represents a solid, and an AQ represents aqueous. Now in class, you're going to be asked to do a lot of balancing review, and that's because that stoichiometry thing that's coming up at us is based upon balancing. And if you can't balance the reaction, everything else is going to be lost. So we're going to work on this a lot next day.